Wants anything to say to these?
Yeah. So this is, so what is this? This is, all this is saying is that we've already kind of crunched this down to something more conveniently expressed than, think what this would look like if we plugged in U into this template. It'd be pretty ugly, wouldn't it? Right? And so what we're saying is, okay, we can write this as the function is 4u over u squared plus 5, where u is this big ugly polynomial, right? Okay. And then we're going to just, all we really want to do is find the value of the derivative when x equals 0. So there's some notational stuff here that we might need to review also. So what does this mean when we say, that's a weird operation? It's a composition, yeah, right? Did you guys ever talk about fog?
Yes.
Yeah, okay.
That's what we
I don't like fog, but it's fine. I mean, that's a fine way to do it. So you know that when you use this operator, this composition operator, that's saying f of g, right? Of x or whatever the independent variable is, x in this case, right? And so another way of saying that would be g of x is just u, so that's the same thing as saying f of u, right? So in calculus, we'd far prefer to think of it this way. That's less complicated looking than that is, agreed? Okay? So then all we have to do here is just apply the chain rule. That's really all it is, right? So we're going to differentiate this with respect to x. Okay, this leads directly into that discussion we had last week, I think last Wednesday, about implicit differentiation, right? All that is, remember, is we're just going to differentiate an expression with respect to a specific variable and not worry about whether or not, well, not really worry about whether or not we've got the equation written explicitly in terms of x from the very beginning, right? We're just going to take the derivative and just see what happens. So if we do that, we end up with, let's start with this expression. On the left, we just get f prime, right? And what we really want here is f prime, we want, dy dx, right? So we really want f prime of x, okay? Equals what? Well, how do I deal with that? Think ogres, right? That was appropriate for playing that music. Thinking ogres, like we say, they're complex. The ogres have layers. What is the outermost layer of this function here? It's quotient, right? It's a quotient of u's. So what, that u is in itself a function of x? The outermost layer, it's just quotient rule, right? So we're going to get back what from the quotient rule? Low d high minus high d low over v squared. Yeah, low squared. Okay, so that gives us low d high is what?
U squared plus 5 times 4.
Times 4
Prime.
u prime, right? See what I'm saying? We get 4.
Yeah.
You're right, we get 4. But the 4 is times a u prime. Now, we'll be able to do something tricky with this, right? But you agree that we actually do have to look inside that next layer there, don't we? Right? Because it's quotient on the outside. But when we differentiate the top, we've got a u prime there. Because we're not differentiating with respect to u, we're differentiating with respect to x. And du dx is not 1, it's u prime, right? Okay, so then you said low d high minus high d low. Well, what's d low?
2u.
Very good. 2u u prime, right? All divided by
U squared plus 5 squared. Quantity squared.
quantity squared. Very good. Okay, good. So now notice what we can do here, though. Notice that whenever we do something like this, this is a pattern that we see. We see a factor of u prime in each of those parts of the top, didn't we? Right? So we could, if we wanted to, just pull that out, right? And we'd end up with, if we did that, what do we get? So then we get,
Log 4, 2.
yeah, u squared plus 5 times 4 minus 8u squared all over u squared plus 5 squared times u prime, right? Okay, well, what is u prime? If u equals this, what's u prime?
4x plus 3.
Yeah. Okay, so we have a couple options here then. All we're trying to do is evaluate this at x equals 0, right? Do I want to go through the process of writing out, of substituting all of this stuff for u and this stuff for u prime and then substituting? I could. That seems like a lot of work though, doesn't it? Is there an alternative?
Plug 0 into the original.
Sure, why not, right? If I'm evaluating this at 0, aren't I really just evaluating like u would just be g of 0, right? And u prime is really just g prime of 0, right? Does that make sense? So let's figure out what those are. What is g of 0 is what? 4. G prime, and that's just u, right? G prime of 0 is what? It's pretty easy, doesn't it? Right? So if we're evaluating this at 0, then we just end up with f prime of 0 equals, well, what do we get? 4 times u is 4 squared, right? So, yeah, 4 squared plus 5 minus 8 times 4 squared divided by 4 squared plus 5 squared, all times 3. Just throw it in your calculator and get a number, right? No big deal, right?
3's the magical number, because the whole trinity,
I thought it's a double.
no,
Okay.
666.
Make sense?
Fourth is the two.
Okay, so a couple highlights there. Just recognize that this has been already kind of simplified for you. It's already been written as a function of u, where u is a function of x. And the other thing really to remember about this is, whenever we do a problem like this, where we're finding the value of something at a specific value of x, do we want to go through the arduous process of simplifying algebraically? Heck no, right? It's way easier to simplify by just plugging in a value of x and combining numbers, right? Okay.
Even 4.
Number 4? Okay, sure. Yeah, that guy? Okay. Okay,
I mean, I got the right answer when I did, I just don't know how I got it.
okay.
It's one of those.
So, yeah, let's go through chain rule on this one, right? So we know S equals cosine theta, right? Okay, and they're telling us that d theta dt equals -6, okay? So by chain rule, if we want to find ds dt, what's that going to be? So we'll just call it s prime for now, right? Is going to equal what? So at the outermost level, what do we have here? We have cosine of something. What's the derivative of cosine of something? Negative sine of something. Well, the something is a theta, right? So now if we look at the next layer, inside the cosine is a theta. So what's the derivative of theta with respect to theta?
-6.
No, hang on. I'm asking something different than what we're going to do in the problem. Just, what's the derivative of theta with respect to theta?
1.
1, right? But that's not what we're doing. We're taking the derivative of theta with respect to t, right? So what is d theta dt? We'll just call it theta prime, right?
Which is -6.
And we know that. Yep, theta prime. So right here, right, this tells us that theta prime equals -6, right? And what is theta? It looks like theta is 2 pi. So I could specifically plug that stuff in and get an answer, right? So we end up with minus sine 2 pi. What is the sine of 2 pi?
0.
0 times negative 6 equals 0. That's our answer.
I was rewriting it as ds over dt equals ds over d theta times.
That's fine.
d
You can do
theta.
that. That's what we did. But remember, we don't really. So that's true. That's true. That was useful to us when we were, for example, we did those couple of problems where we had a parametric system where they both were. We had x's and y's written as functions of t, right? And so we could differentiate x prime and y prime separately and combine them in that way. But that's not the way we use the chain rule when we're doing stuff like this, right? When we're doing stuff like this, we're thinking about just differentiating in layers. For each layer, we're going to get a link in the chain, right? So think back to the stuff we did where I gave you some, remember that huge nasty one that had all those layers? And we just looked at it, you know, at the outermost layer, it was just this really complicated thing to a power, right? So the first layer was just hand to the 6th is just 6 hand to the 5th, right? Times, then we look inside. What's inside the power, right? We just work our way down like that, okay? Does that make sense? What you did is fine. This technically is, if you said, I'll kind of draw a way to correlate the two. So you just said ds dt equals ds d theta times d theta, dt. And this is just that, right? And this, oh no, there we go. This is just that. Still works. It just is not as easy to think about it that way. Okay, so how about
Can you actually, bro? So on one of them, I had like the quantity 13 plus 6x square rooted,
mm-hmm.
and I have to find the derivative of it.
Mm-hmm.
For some reason, I couldn't. Would you use chain rule on that? Or?
So like this one?
Yeah.
Okay.
Yeah. Can you just?
Right, so all we're gonna do then is, yeah, but you do have to use chain rule because there's 2 layers here. We'd want to rewrite that. The square root of hand can be rewritten as what?
So the quantity to the amount.
To the 1/2, right? So I've got hand to the 1/2. And so I'm gonna have 2 layers to that. I'm gonna have, what's the derivative of hand to the 1/2? Well, that's
1/2 hand
to 1/2 hand to the negative 1/2, exactly. Okay, so there's the first link, times the derivative of what's inside. Well, what's the derivative of 4 plus 4t in this case with respect to t? 4. So those are my 2 links, okay? Mm-hmm. And then we're just evaluating these, whatever answer we get, that's velocity, isn't it, right? Because this is position, right, and velocity is the derivative of position, it's ds dt, right? And so we would just be evaluating that derivative when t is 3.
So you just plug in 3.
Yep, plug in 3 to that derivative, exactly.
Could you, since you would get like 1/2 the quantity blah 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 hand to the negative 1/2 times 4,
Mm-hmm.
could you just do 2 times the quantity hand to the negative 1/2?
What do you mean, how come 2?
Because 4 times 1/2 is
Oh,
2.
yeah, sure, that's what you, when you simplify, that's what you'll get, absolutely, yeah.
Making
Mhm.
sure.
Yeah, you're right. I see where that was coming from. Okay, so that should hopefully, and then a problem, I realize this is kind of a harder one, but it's not a big deal, right? Because this is just like the problems you did earlier with derivatives that didn't require the chain rule. All this is, I mean, think about, I'm not gonna go through the whole thing, but let's just talk process for a second. So we'd wanna add the implied parentheses there, right? And really then this is just 18 times cotangent of hand, right? So we wanna find, if we wanna find the tangent to the curve, we're just calculating y prime, right, dy dx. So I've gotta have 2 links in my chain. I've got the derivative of cotangent, right? which is what?
Secant times that?
No. Negative cosecant squared, right, of hand, right? And you gotta know those. I'm gonna make you guys, we're gonna do a little quiz with that. I better get that going. Times the derivative of what's inside, which is what? What's the derivative of pi x over 36? It's really just pi 36x, right? What's the derivative of that with respect to x? Pi 36, right? Just that. So we'll multiply it times that, and that's the derivative function. But we want to evaluate it at x equals 9, right? So the slope of the tangent line is just going to be whatever that derivative is when I evaluate it at x equals 9, correct? What are the ingredients of a tangent line, of any line? A point and a slope, right? Well, there's our slope. Our point is x equals 9. How do I find y? Plug it in, right? To the original function and find y. Then I've got a point and a slope, and they're ugly potentially.
Oh, so when it says y, it's asking for the line?
Yeah, we want the,
Okay.
you want the, when we say tangent to the curve, that implies tangent lines. We want to fill in the blanks, y equals mx plus b, you know, with your specifics. Okay? All right, how about 2-5? Would that be worth taking a peek at, maybe, I'm thinking?
Yes.
Really? Disable it now.
Why does it care about pop-ups?
It needs to be able to access them. How do I do that without having to go clear in? And is there a way I can
What are you
just
trying to do? Pop-up block.
enable pop-ups?
It should say
Just go to settings.
Yeah, but it seems like there ought to be a way to do that quicker. I guess not.
Take 15 minutes to figure out how to do it faster.
It would be nice to do faster. So where is that? Pop-ups.
What do you need the pop-ups for?
Content settings. Pop-ups.
manage exceptions.
Yes,
Oh,
manage
settings.
exceptions. And this is,
Math stuff.
yeah, so I gotta go.
It's already allowed. Math Excel for school, it's right there.
Well,
Yeah, it is. Huh.
Why don't you want pop-ups?
No, he does want.
I
No,
do.
yeah, I know, but why would you not want any at all?
Oh, so you just don't get annoying ads popping up all the time trying to sell you stuff.
I think it might be worth just allowing all of them, because it's very possible that you might have to like remove every individual thing.
I'm just gonna, yeah, I can change it later.
Most of
I'll
them-
just do
most
that.
of them don't.
Yeah, I know, but I mean, any that do, it's pretty, not exactly too much of a bother.
Well, usually when they do pop up, they're not that reputable sites in the first place.
Exactly.
Okay.
I go only on the most high quality sites, so I wouldn't know.
You have to be high quality.
You know what, Michelle?
Okay, so these, use implicit differentiation. This was really not a big deal. What did we do?
You have to do the.
Right.
I figured this out. Oh, it was the one where the Y prime.
Yeah, the white primes are just gonna pop out, aren't they? Right? So this is the one, let me find the best one to do here. So. Okay. Let's find a really nasty one. Okay, that's a candidate. Yeah, that one. That's the one I want to do. Okay. Oh, these are not very fun. Not very fun. I mean, it's good to know how to do. You need practice. I already know how to do them. So for me, I just don't like doing them. Because I already know how. I don't need the practice. I'm going to do it for you anyway.
Doesn't make it better, dude.
Yeah. I'm just really excited to get on to the next section because it's so cool. But this is important. We gotta make sure we got this.
This is
That's
like
what
the
you say
next
about
one.
every section. So
Yeah,
It's pretty true.
yeah.
just
Well, this was, you have to admit, this was pretty cool when we did the deal with the y equals, or the x equals y squared. And we were able to show that, I thought that was pretty, thought that was pretty slick. Okay, so,
Oh, yeah, I remember that.
yeah,
Oh, yeah. Oh, yeah.
Oh, yeah,
Oh,
I
yeah.
remember that.
Oh, yeah, I remember.
Cause I had to look down at my paper.
Did it? Anyone?
Wait, say it again?
You did it? Yeah.
I didn't finish it.
It was
It's
funny.
just not funny.
It's too late. You lost your chance.
okay, so let's try one like this. Let's just do, let's do something like this, where we have x squared plus y squared equals 25.
Wait, that's not,
It's a little different. We'll just do this one, similar.
but.
So
like,
we wanna
it's the same
find-
thing. We're finding the,
We're gonna find, yeah, we're gonna find, what I wanna find is, let's just find y double prime, find the second derivative, okay? So to find the second derivative, we gotta find the first derivative, right? So we're gonna differentiate implicitly. Well, what does the first term give us if we implicitly differentiate with respect to x?
2x.
2x. How about the next one?
times equals 0.
No.
Oh, no, y prime,
Y prime
right, because we were doing it, yes.
equals
Good job, Kylie.
0. Good. So we can divide both sides by 2, get rid of those, right? And now we gotta solve for y double prime. Okay, so what about that? So to solve for y double prime, we have an option here. We could, if we wanted to, we could scoot over this way and isolate y prime. And we would get, if we do that, y prime equals negative x over y. Everybody agree? If I subtract x and divide by y, to isolate y prime.
Oh.
Everybody agree?
Yeah.
And so I could, I could just now differentiate again, but in the spirit of implicit differentiation, let's not. Let's just have at it again. Let's just differentiate both sides of this equation implicitly with respect to x. So what do we get from the first term? 1, because the 2's are gone, right? Plus, well, we're gonna get some stuff here because I've got a product, right? So I'm gonna go ahead and open up a set of parentheses because we know we're gonna have product rule. Okay, so what's the product rule tell us about the derivative of y times y prime?
Y times y double.
Okay, I'm gonna get y times the derivative of y prime, which is y double prime, okay, plus, yeah, y prime times the derivative of y, which is y prime, so that's really just y prime squared, right? Okay, and it turns out I really didn't need that set of parentheses, did I? Because I'm just adding stuff. And that's all equal to
0.
0, okay? So why don't we get rid of those unnecessary parentheses? Let's get rid of those. And so we're just trying to now isolate y double prime, right? So what are the steps to get the y double prime by itself?
You just, algebra.
Yeah.
Yeah.
So I'm just gonna subtract away this stuff and divide by y. Everybody agree? Okay, so then I'm gonna get y double prime equals negative y prime squared minus 1, all divided by y, right? Okay, well, that's kind of my answer, right? Now, probably what we want to do, though, we probably don't want to write our answer in terms of y primes. It's okay to write it in terms of x's and y's, right? But writing it in terms of y primes is, I mean, we could say this is our answer where y prime equals that. But if we're explicitly told, as you will be, to write your answer in terms of x and y, what would I do?
You would substitute in it.
Yeah, just substitute, right? And so we'd end up with negative the quantity minus x over y squared minus 1 over y, right? And if we simplify, that's just x squared over y squared, right? So I get negative x squared over y squared, because we gotta multiply that negative by negative one. What's that?
It's all, oh wait,
No,
never mind.
it's for-
Yeah, so I square it, which makes it positive, then I've still got that negative coefficient out front. Okay, minus one over y. Gotta get a common denominator on top, so I'd write that as just y squared over y squared, right? And that's gonna give us negative x squared minus y squared over y squared, divided by y over one means times one over y, right? And so our answer ends up looking like negative x squared minus y squared over y cubed. So that's y double prime in terms of x and y.
How do you go from first one to the second one?
Okay, because we just multiplied this one, we just multiply by y squared over y squared to get my common denominator of y squared. Right? Flip and multiply by the bottom.
and so that would be y double prime.
Mm-hmm. So that's y double prime, right? Okay. Make sense? All right. So how we doing on time? 2 minutes. Is it seriously 2 minutes?
Yeah, 1 minute.
It's true.
Man,
Sorry, 1.5.
we need